Dear students, welcome again to the online class of HS Second Year Science. Myself, Dr. Ashim Kalyan, Associate Professor, Department of Physics, SS College Hailakandi. In the last class, we have discussed about atoms and molecules. We have learned what are atoms and molecules and how they form. Moreover, we also discussed about various models associated with atom to describe its structure along with their limitations. Today, I am going to discuss elaborately about Bohr's theory and we will discuss how this theory can explain the hydrogen atom and its spectral lines. So, first of all, we start from the assumptions of Bohr's theory. According to Bohr model, an electron can revolve around the nucleus only in certain permissible orbits called stationary orbits. They do not lose any energy when revolves in a stationary orbit. The stationary orbits are not arbitrary, but only those orbits are permissible in which angular momentum is integral multiple of h slash or h by twice pi. So, angular momentum is quantized. But in the transition of orbits, that is when an electron jumps from one orbit to another orbit, then and only then it can emit light or absorb light. Classical laws of physics do not apply to this transition between the stationary states because we have observed in the Rutherford model that classically the energy continuously radiates when revolves around the nucleus. Now, what is classical atomic model? Classical atomic model is the model of atom in which it follows the classical laws, that is Newton's law. Here we consider an atom as a planetary system. The Newton's second law of force of attraction on the electron is acted on this nucleus and electron system. Precisely, we can say that Coulomb's law is applicable in the atomic system, that is, the force of attraction between electron and the nucleus is governed by Coulomb's law. Here is the force, and this is the Coulomb's law 1 upon 4 pi epsilon naught E square by R square. Since in this model we assume that electron revolves in a circular orbit, so it requires a centripetal force, and that centripetal force is mv square by r. So when you balance these two, then it becomes 1 upon 4 pi epsilon naught E square by R square is equal to mv square by r, where b is the tangential velocity of the electron. Now from this equation, here this is the simple model of the equation, simple model of the atom in which the electrons are revolving around the nucleus. Now from this equation we will derive the expression for velocity, and this is the expression for velocity because you can cancel this r with this square and simply By simplifying, B is equal to square root of E square is E, and here root over 4 pi epsilon naught R, and this is the M. So B is equal to E by root over 4 pi epsilon naught mr. So if we know the velocity, then we can also get the kinetic energy, and we will also find the potential energy because force is given. So kinetic energy is half mv square, that is half of b square, half of e square by 4 pi epsilon naught r. So the total energy is actually nothing but the kinetic energy, sum of the kinetic energy and potential energy. So E is equal to K plus B. K is the kinetic energy and B is the potential energy. From this force, if we multiply distance with this force, then we will get the potential energy. Then it will be simply 1 by 4 pi epsilon naught E square by R with a negative sign, because here electron is associated with negative charge. So this is the kinetic energy and this is the potential energy, and the total energy is minus E square by 8 pi epsilon naught R. What is the significance of this negative energy? The significance of this negative energy is that we have to give energy to disrupt the system, that is, the system is bound one. This is negative, so the system is bound system. Now we will discuss the different consequences of Bohr model. In the Bohr model, or in the Bohr assumption, we have the angular momentum L is equal to mvr is equal to nh slash. So velocity is simply v is equal to nh slash by mr. Also, in the last slide, we obtained v is equal to e by root over 4 pi epsilon naught mr, and here is v is equal to nh slash by mr. So we can equate these two. So from these two equations, from this equation and this equation, we get n square a slash square, square of this is equal to square of this, square by 4 pi epsilon naught mr. Solving, here we can cancel r and r square. Solving for nth orbit, that's why we put here rn. In the suffix we write n for nth orbit. Solving for rn, we get rn is equal to n square n naught. This is your n square, and this terms a slash square, m square, 4 pi epsilon naught, these are constants, and this constant is n naught, where n naught is 4 pi epsilon naught a slash square by m square. This is a constant, and this constant is called Bohr radius. It is the diameter of hydrogen atom in its lowest energy or ground state. Now we will find the value of Bohr radius. The radius of hydrogen atom in the stationary states is already obtained. We have already obtained. Rn is equal to 4 pi epsilon naught n square s square by me, that is n square n naught. Where the Bohr radius is given by, that is n naught is given by, n naught is equal to 4 pi epsilon naught s square by m square. Putting the values of 4 pi epsilon naught s square, m and e square, we get these are the values of these constants, and putting this value we get, this is nothing but 0.53 into 10 to the power minus 10 meter, that is 0.53 Armstrong. So the smallest diameter of hydrogen atom is, that is in its ground state, twice R1. This is the, for here R1 means the ground state, that is R0 or N0. Twice R1 is equal to twice N0. is of the order of 10 to the power minus 10 meter. That is the atomic radius, that is the radius of or diameter of hydrogen is approximated to the order of 10 to the power minus 10 meter, that is in the Armstrong order. Here n is equal to 1 gives its lower energy state called ground state. Now we will calculate the energy of hydrogen atom from this Bohr radius. The energy of the nth state of hydrogen atom is given by En is equal to minus square by 8 pi epsilon naught Rn square. This En is nothing but the total energy that we obtained in the previous slide, where it is given E, and here we put the value N for representing nth orbit, energy of the nth state, and that's why we also put here Rn. So En is equal to minus square by 8 pi epsilon naught Rn, and putting the value of Rn, that is n0 n square, we get E square by 8 pi epsilon naught n0 n square. This E square by 8 pi epsilon naught n0 are constants, and that is represented by E0. So it is minus E0 by n square, where E0 is equal to 13.6 electron volt. Just putting the values of E epsilon naught and n0, we will get the value of E0, which comes out to be 13.6 electron volt. Now the emission of light occurs when an atom decays from its excited state to lower energy state by the relation H nu is equal to ENI minus ENF. That is, if there are two energy states E2 and E1, then the energy difference comes out as electromagnetic radiation, as that is E is equal to H nu. The difference between energy levels, that is E, becomes equal to H nu, where H is called Planck's constant and nu is the frequency of emission. Solving for nu rather lambda, we get 1 by lambda is equal to nu by c, 1 by lambda is equal to nu by c, and putting the value of ENI and ENF, we get this equation. Simply putting these values, En is equal to this, n square for Ni we will write n I square, and for NF we will get NF square. So putting this value and subtracting, we get R capital R into 1 by NF square minus 1 by Ni square, where R is nothing but this constants, and this constant is known as Rydberg constant, where R is equal to m into the power 4 8 epsilon square Ch cube, and its value turns out to be 1.097 into 10 to the power 7 meter inverse, and is known as Rydberg constant, and lambda is the wavelength of the line emitted. But 1 by lambda is represented by nu bar, which is also known as wave number. Sometimes we can represent the above equation in terms of wave number also. The wave number is nothing but the number of waves per unit distance. Here the energy is expressed in terms of meter inverse. That's why the number of waves, we count the number of waves per unit distance. And the above equation is known as Rydberg formula for hydrogen atom spectrum. Now we will discuss the spectral series of hydrogen atom. So we have seen that Bohr's theory can calculate the energy, and the value of energy that comes out in the ground state is minus 13.6 electron volt, and this energy is found to be experimentally correct. So Bohr model can successfully explain the basic hydrogen atom. Now we will discuss the different spectral series of hydrogen atom. First one is Lyman series. The spectral lines emitted due to the transition of an electron from any outer orbit, that is Ni is equal to 2, 3, 4, 5, etc., to the first orbit, that is Nf is equal to 1, from a spectral series, form a spectral series known as Lyman series. The wave number of the spectral line of Lyman series is given by, in the Rydberg equation we can write 1 by lambda is equal to r into 1 by 1 square. That 1 square comes for Nf square, and second term is minus 1 by Ni square. Here the value of Ni will 2, 3, 4, 5, etc., because we have already mentioned that the Lyman series will be only visible or only observed when the transition takes place from second, third or fourth orbit to the first orbit. Now we can calculate the longest wavelength and shortest wavelength to observe the range of the spectral series. The longest wavelength of spectral line of Lyman series is emitted when the transition of electron takes place from Ni is equal to 2 to Nf is equal to 1. That is, when the energy transition takes place between two adjacent orbits, then the wavelength will be, energy will be minimum and wavelength will be maximum, because E is equal to h nu or E is equal to hc by lambda. So energy is inversely proportional to lambda. When energy is minimum, wavelength is maximum. So when the transition between two levels is less, then the wavelength will be large. So here the minimum level of transition is from Ni is equal to 2 to Nf is equal to 1. So in that case, putting the values, we get 1 by lambda max is equal to r into 1 by 1 square minus 1 by 2 square, that is r into 1 minus 1 by 4, that is 3r by 4, or lambda max is equal to 4 by 3r. Putting the values 4, 3, and below feedback constants 1.097 into 10 to the power 7. So calculating this value, we will get it as 1.215 into 10 to the power minus 7 meter, or 1215 Armstrong. The shortest wavelength of the spectral line of Lyman series is emitted when the transition of electron takes place from Ni is equal to infinity to Nf is equal to 1. That is, when the energy difference is larger, then the wavelength will be small. So in that case, from Rydberg's equation we can write 1 by lambda mean is equal to r into 1 by 1 square minus 1 by infinity square is equal to r into 1 minus 1 by infinity, that is r. So lambda mean is equal to 1 by r, that is 911 Armstrong. So the wavelength ranges from 911 Armstrong to 1215 Armstrong. This range of wavelength lies in between the ultraviolet region of electromagnetic spectrum. That's why Lyman series is available in the ultraviolet region. Next one is Valma series. This spectral lines emitted due to the transition of an electron from any outer orbit, that is Ni is equal to 3, 4, 5, 6, to the second orbit Nf is equal to 2, forming a spectral series known as Valma series. Like in the previous section, that is, as we calculated the wavelengths in the Lyman series, the wave number of spectral line of Valma series is given by 1 by lambda is equal to r into this, and we can calculate the longest wavelength spectral lines of Valma series when it transit from Ni is equal to 3 to Nf is equal to 2 as 1 by lambda max is equal to r into 1 by 2 square minus 1 by 3 square, that is r into 1 by 4 minus 1 by 9 equal to 5r by 36, or lambda max is equal to 36 by 5r, and that comes out to be 6559.2 Armstrong. Whereas the shortest wavelength of spectral lines of Valma series is emitted when the transition of electron takes place from n1 ni is equal to infinity to nf is equal to 2. That is, here for calculation of shortest wavelength, the energy difference should be large. So in that case, 1 by lambda mean is equal to r into 1 by 2 square minus 1 by infinity square, that is r into 1 by 4. So lambda mean is equal to 4 by lambda, 4 by r, that is 4 into 9.1 4 into 911 Armstrong. That comes out to be 3644 Armstrong. So what is the range of this Valma series? Here the range is from 3644 Armstrong to 6559.2 Armstrong. That is, this wavelength ranges from 3500 to 7000 Armstrong, which is in the visible range of electromagnetic spectrum. So Valma series lies in the visible region of the electromagnetic spectrum. The next series is Spectral Series. In this series, the spectral lines emitted due to the transition from electron from any outer orbit, that is ni is equal to 4, 5, 6 etc., to the third orbit nf is equal to 3, from a spectral series known as spectral series known as Spectral Series. The wave number of spectral line of Spectral Series is given by is similar to the previous ones, that is exactly similar to Lyman series and Valma series. Here we only change the value of nf. 1 by lambda is equal to r into 1 by 3 square minus 1 by ni square, where ni is equal to 4, 5, 6, 7 etc. We are not going to calculate the longest and shortest wavelength of the spectral line of Spectral series, because we have already learned how to calculate the shortest and longest wavelength, and rather we have learned how to determine the range of wavelength of a particular series. So in this case, the longest and shortest wavelength of spectral lines of Spectral series are lambda max is equal to 18,741 Armstrong and lambda mean is equal to 8,199 Armstrong. This series lies in the infrared region of electromagnetic spectrum. The next series is bracket series. The spectral lines emitted due to the transition from an electron from any outer orbit ni is equal to 5, 6. Here the number of orbit increases in each series. Lyman, in case of Lyman it was 2, Valma 3, Kalyan 4, and in that case bracket it is 5, starting from 5. Any outer orbit ni is equal to 5, 6, 7 to the fourth orbit, that is nf is equal to 4. That is final state is 4, fourth orbit, and initial stage is 5th or 6th onward orbits. This form the bracket series. Here the maximum wavelength of bracket series is 40,589 Armstrong and minimum wavelength of bracket series is 14,576 Armstrong. So this series is also lies in the infrared region of electromagnetic spectrum. The last one is Quant series. Here the spectral lines emitted due to the transition of an electron from any outer orbit ni is equal to 6, 7, 8 etc. to the fifth orbit nf is equal to 5, forming a spectral series known as Quant series. In this case the maximum wavelength is 74,536 Armstrong and minimum wavelength is 22,775 Armstrong. So this wavelength range lies in the far infrared region of electromagnetic spectrum. So we have learned the Lyman series lies in the ultraviolet region, the Valma series lies in the visible region, Kalyan series lies in the infrared region, Beckett series lies in the infrared region, and Pant series, the last one, lies in the far infrared region of electromagnetic spectrum. Now we will show the line spectra of hydrogen atom, that is on the energy level diagram, how energy transits and forms different spectral lines. This is the diagram. This is the energy axis and this is the number of orbits. So when electron jumps from n is equal to 2, 3, 4, 5, 6, it forms the Lyman series. This is the Lyman series. N is equal to 2 to 1, 3 to 1, 4 to 1. This forms the Lyman series. And when electron jumps from n is equal to 3 to 2, 3, 4, 5, 6 to 2, second orbit, then it forms Bohr series. And next one is Spectral Series, and so on. This is the spectral series of hydrogen atom on the energy level diagram. Next one is Kalyan, Beckett and Pant. Here we show only 3 energy levels. Here the atom will remain in the excited state. Actually all the atoms remains in excited state for a very short period of time, and it subsequently returns to the ground state or lower stationary state by emitting photon. So we have discussed how Bohr's theory can explain hydrogen atom and its spectral lines. But we have also discussed in the previous class about the limitations of Bohr's theory. Bohr's theory is not perfect one, and there are several limitations of Bohr's theory. Even it cannot explain the fine structure of hydrogen atoms. So only quantum model can explain successfully the atomic structure. So for today, this is the end of my presentation. Thank you.